Alright, what's going on, you guys? Another LeetCode video today. This one's called kth largest element in an array. So we're given an integer array nums and an integer k. They want us to return the kth largest element in that array. And then, a distinction to make here, it's going to be the kth largest element just in the sorted order, not the kth distinct element, so we don't care about skipping over like duplicate elements or anything. It's just going to be that absolute, kth largest element. If there were like 3 10s that were the largest element, and they want the second largest element, it would still be 10. So yeah, let's get into the whiteboarding for this. So a couple thoughts. They just want their array is given to us unsorted, right? So, a naive approach could just be to sort the array, right? That would require big O of n log n time, right, for sorting, using like the fastest sorting methods, and then you could just use a constant index lookup to get that kth largest value after that. So that's pretty good, but could we do better? You could also use a min heap to store the kth largest elements, and then just return the bottom of the heap. That would require big O of n log k time, right? Because pushing and popping from a heap is log k. If there was k elements in the heap, then you have to do that n times for the number of elements. So that's pretty good too. But we can actually improve on both of those solutions. So if we take advantage of one of the partitioning subroutines of quick select, we can actually do this on average with big O of n time, right? The worst case, it's technically going to asymptotically be bounded by big O of n squared, but that's going to be rare. On average, it's going to be big O of n, which is better than both of these solutions. So also, not to mention, it's going to have constant space, right? This solution with the sorting is constant space, but this one is not, right? It's going to be big O of k, right, for a heap of k elements. But this one will, this will be big O of 1, because we're not going to have any extra data structures for the quick select. So let's go over that quick select implementation. And we're not fully using quick select. We're just using that subroutine, like a partitioning subroutine, that's going to basically partially sort the array for us, only sorting a part of the array that we're interested in, right? We don't need to waste time sorting the entire thing. So basically what we're going to do is, we have this input array. I think for this example, k was 2. Let's double check that to verify. Yes, k is 2. It's just this first example. So the output is 5. Obviously, that kth second largest element is going to be 5. The largest was 6, but let's see why using this quick select algorithm. So what we're going to do is we need to choose a pivot, right? The idea is going to be to basically choose a pivot, move all of the elements greater than that pivot on one side, all of the elements less than that pivot on the other. Then the pivot we know will be in the correct place. And then, depending on, we'll check the pivot's index once we know it's in the right place in relation to the index of where the kth largest element should be. And then depending on that, we can either just return the value at the pivot, or we can keep searching on the side of it where we, at that point, know we need to look, right? So we can choose any pivot randomly. I'm just going to choose the first element here. So we're going to choose this as our pivot. We don't need to worry about the pivot in our pointers, right? So we're going to skip over this 3 and just have our left pointer here at first and our right pointer here. Okay, so, and let me actually use a different color, because I used red for those indices, and it's not really related. Sort of is related because they're pointers corresponding to indices, but anyways. So the first thing we're going to do is we're going to just look at both of these values, compare them to the pivot, right? So we're going to check okay, is the value of this left pointer less than our pivot? We're also going to check, is the value of this right pointer greater than our pivot? If both of those are true, then we can just swap them, right? So we're going to go ahead and swap both of these. So we're going to have a 4 here and a 2 here. All right, and then we can just increment and decrement them respectively, until they're overlapping. So now we can just do the same comparison. We're just going to check if this value is less. By the way, we're going to put the smaller values on the greater values on the right side, or the greater values will go on the left side of the pivot point. The smaller values will go on the right side of the pivot point. It doesn't really matter which way you do that, but you have to decide one way or the other, right? So again, we're going to compare these. 1 is less than 3, and then 2, we never decremented this r, so let's make sure we do that. So 1 is less than the 3, 6 is greater than the 3, so we can just swap these. Okay, and then we increment and decrement respectively, same thing. So now they're going to be overlapping, which is fine. So we're going to check, okay, is 5, is the left value less than this? No. Well, there's no point in evaluating both of those, right? Because the first one already doesn't work. So there's going to be some more conditions after this, right, which are kind of going to be the inverse. We're going to check, okay, is the left greater than 3? Yes, it is. If the left value is greater than that pivot value, we're just going to increase that left pointer. So, and we're going to do the same with decrementing the right pointer if the right value is less than the pivot, but it's not. So the right value will just stay as is. Okay, and then there's one final thing we need to do. So we're done looping because these have now overlapped. But before we can return, we've got to swap the this right element with the first element that we started with, wherever our left pointer started, which was at our pivot originally. So, I mean, technically it was here, but we do want to start at the beginning of this range, and the pivot is included in that range. So it's going to be where the pivot was, right? So we're going to swap this right value with the pivot value. So just the 5 and the 3. So this 3 is going to go here, and then notice what that does. This is now perfectly partitioned. We know our pivot is here, right? That's going to be in the correct place because all the values greater than it are this way, all the values less than it are this way. So we're done with this partition. We're going to return the index of the right pointer because that's where the pivot index is. So now we have an index that equals to 3, and we're going to do some checks with that. Or actually, it's equal to 0, 1, 2, 3. Yeah, it's equal to 3. So we're going to do some checks with that. All right, so we're basically going to check if, because we need to basically see where this pivot is in relation to the kth largest value. So the index we're looking for the kth largest value, like if this array was sorted, the greater values are over here. The index we're looking for is going to be k minus 1, right? Because this is a 0 indexed array. So if we're looking for so if k equals 2, the second greatest value here would be at index equals 1, right? So this is what we want our index to be. So this value isn't necessarily sorted, right? But we know this is the only value that's sorted here. This is our index 3. We know our pivot is going to be somewhere in here, or the kth largest element is going to be somewhere this way, specifically on this index. So we basically need to do the same partitioning, but with this range, right? So let's go ahead and do that. So we're going to have our new left and right pointers are going to be, let's see, here, and then 1 minus that pivot. So here and here. So we're basically going to do the same process again with the pivot, but over here. All right, so we're going to check, is this value less than 5? Yes, it is. Is this value greater than the pivot 5? Yes, it is. So we can just swap those. So we're going to have 6 and 4, right? I believe that was right. Yeah. Okay, so then we can increment and decrement respectively. They're going to be overlapping, obviously, so we're going to be done here. We're basically, you know, there's one more thing we have to do. We have to swap this right value with the first value, right? So that's going to be 5 and 6 and 5, right? We just swap those, and then we're going to return the index of the pivot, which is now here, right? So we're returning I equals 1. So, and that is I don't like the way that I looks, but I equals 1. Okay, so now we're checking, right? Basically, is this I equal to where we expect the kth largest value to be? And remember, we expect it to be at this 1 index. And sure enough, we have I equals 1. We know the pivot is sorted, so we can just return the value at I equals 1 now, which is obviously correct. It's going to be this 5, which is the output here. So once again, on average, this is going to take big O of n time. The worst case is big O of n squared, but that's rare. So that's why this is optimal to min heap and then just the regular sorting. But anyways, yeah, let's get into the code now. So the first thing that we want to do is we need some pointers, right? So let's have a left pointer, a right pointer, which will just be nums.size -1. And then we also need a variable for the result. So we're just going to loop while true, because remember, we're looking for our pivot point to be where we expect the kth largest value to be if the whole array was sorted, right? So we're going to loop while true, and we're just going to check, like, first of all, we need to partition the array and figure out where that pivot point is, and then, you know, sort the values on either side of the pivot. So we're going to say int I, that's going to be where the partition is. And we're going to write a function called partition that's going to take the array and then the range in which we are partitioning around a pivot, right? So it'll just take those 3 parameters, and we'll implement that in a second. But first, let's just implement this outer code first. So to check, you know, if that I, so if I is equal to k minus 1, right? That's where we expect the kth largest element to be. If that pivot, you know, is where we expect it to be, then we can simply set our result equal to whatever the value is there at that index, and then we can just break from this loop and return the result, right? Otherwise, we need to search. You know, we need to continue partitioning on either side of that pivot. So otherwise, you know, if I is less than k minus 1, then we need to search the left side, right? So we're just going to set the left we're going to set the left pointer equal to whatever that index is plus 1, right? Because basically what this is saying is that our index is less than where we expect this to be. So we need to go ahead and continue searching on the right side, basically to increase the number of, or basically to continue sorting on the right side, you know, where the smaller elements are. So Otherwise, we don't need an else here. The only other option here is if the index is greater than where we expect that pivot to be. So otherwise, we're just going to do the opposite, right? So we're going to search the left side by setting r equals to I minus 1, right? 1 directly below that pivot point index. So yeah, that's it for the outer code here. Now we need to code that partition function, right? So we're going to make that a private function method, and it's going to return integer, right, which is the index of that pivot point. So, and it's once it's been sorted. So we'll call this partition. It's going to take a vector of integers by reference called nums, just that input array, and then a left pointer and a right pointer. Okay, and then the first thing we want to do is just remember where we need to remember where the pivot point, or basically, what is the index of the pivot point or what's the pivot point we're choosing, right? So that is going to be, remember, we're just choosing the first element for our pivot point. So we can say int pivot is equal to nums L. Okay, and then basically we also need to remember where we started our partition, just wherever the beginning of that range is. So I'll just call that begin, and we'll set that to L. And then we actually want to have increment L by 1, right, to get it 1 after that initial pivot point. So then what we're going to do is we're just going to say, while those pointers are not overlapping, so while L is less than or equal to R, and then we're going to basically, the first condition is we're going to check, if they're both on the wrong side of the partition, then we can just swap them, right? So if pivot is greater than nums L and pivot is less than nums R, right, then we just swap them. So we'll say swap on nums L and nums R, and then we can increment and decrement. So we're incrementing L and decrementing R. Okay, after that, we want to see, so if neither of those are true, or even if they were both true, we're still going to try to move the left element and the right element, right? So if nums L, so this is like the opposite, and actually let's do it consistently. So if pivot is instead less than or equal to nums L, then we're just going to increment the left pointer, right? So let's just make this a one-liner. So L plus plus, and then the inverse of that, right? So also if pivot is greater than or equal to nums R, then we can decrement R. So after that, the very last thing we need to do is just swap the whatever that beginning, wherever left started, we need to swap that with the right pointer, and that'll get our pivot in the correct place. And then we can just return that index of our pivot. So that's going to be the right pointer. So that's pretty much it for the code. Let's go ahead and run this. So yeah, hopefully this video helped you understand kth largest element in an array better. If it did, leave a like and subscribe, and I'll see you guys in the next video. Peace.